All right, all the other questions that we've gotten to up to this point are on a couple of other videos that are already posted from our quiz review. So I'm going to start with this one. I believe it's new. Again, it's math questions. So anytime we get a math question, we need to list out what's given to us and then hopefully use our formulas up here to be able to figure out which ones we've got. So we've got a car starting at rest. Remember, this is kind of important because if it starts at rest, this initial velocity is going to be 0, which may be useful. It accelerates 10, and we've got a time of 20 seconds, and we're asking about a distance. So let's list these out. So we've got an initial velocity 0. I've got an acceleration, which is 10. I've got a time, which is 20. And we're searching for a distance, which I don't know. So let's look through and see what we might be able to use. And let's chart with this one. So distance is VIT. Let's see, do we have a VI? Yep, we've got a VI. Do I have a T? Yep. And do I have an A? Yep, we've got everything we need for this one. So we can actually use this formula. That's what we really need to do, is to look, and if we can substitute numbers in for all the other variables, we can use the formula. So so distance is VI, which is 0. So if this VI is 0, then the whole thing is going to be 0 and nothing's going to be happening there. Excuse me. So that gets us to 1/2 A, which is 10, and then T, which in this case is 20. And that 20 needs to be squared. Don't have a calculator handy, but if I do 20 squared, that's going to be 400. And then half of 10 is 5. And if I multiply those together, should get 2,000. It goes back to how far. So we're looking at whatever units of distance were in the question, and this will be a meter for us. So again, our how-to is to use the correct formula, and then our answer would be over here. Using the same formulas, we have another question right here about acceleration, a car traveling 5 meters per second. So again, let's list out what we know. So if it's 5 meters per second, that's going to be our initial velocity. It accelerates at 10 meters per second. That's an acceleration. It goes 200 meters. That's a distance. And then the final thing is that we don't know is how fast is it going, and that's going to be our final velocity. So I'm trying to figure out a final velocity. Again, let's see what all we have. I got a VI, an A, and we've got a D. So can I use this one? I can't use this one because I don't have a time. So we can eliminate using that one. The one down here in the bottom, the VF is squared, so I don't know that VI. We do know A, we know, and D we know. So we can actually use this formula. It's a little bit more complicated, but fortunately we're just solving for VF, which is over here by itself. We're solving for something over here. It gets a little bit more complicated, moving things around. But VF squared is VI squared, which is 5 squared, plus 2 times 10 times 200. So 5 squared is 25. 2 times 10 is 20. Just kind of working the math out here. 20 times 200 is going to be 4,000 plus the 25. Looks like it's going to be 4,025 if my math is correct on that. But that should be how we get the formula. Oops, I almost made a mistake because this is VF squared. So VF squared, which is why it's important to keep writing all this down and double check what you've got. So I've actually given what VF squared is, but we want VF. So to unsquare something, we take the square root. Just like to undivide something, we multiply. To unmultiply, we divide. Opposites, adding and subtracting. So if I need to go from VF squared to VF, then I have to take the square root of it. All right, so if I take the square root of this side, that's going to give me VF, and then I would have to take the square root of 4,025, which again, I don't have a calculator with me right now, and I can't do that math. but that ends up being what our answer should be if you have your calculator putting that in. So the square root of 4,025. So one of the things to keep in mind if you end up having to use this formula is that when you do all the math on the right-hand side, you're not done. You still need to take the square root of that answer so that you can turn your VF squared back into VF. So be careful with that one. All right, most of the rest of these are just concept questions. So this one says, during acceleration, does the change every second, this is worded kind of awkwardly, how does the speed change, basically is what it's saying, and how does the distance change? So if we have an acceleration, for example, 10 meters per second squared, that means after 1 second, 2 seconds, 3 seconds, kind of what's going on. So at 0 time, our speed would be 0. After 1 second, it would be going 10. After 2 seconds, it's going 20. After 3 seconds, it's going 30. So you can see the speed goes up constantly. So it goes from 0 to 10, 10 to 20, 20 to 30. Every time it goes up by 10. And that's what the acceleration is telling us. It tells us the change in speed every second. So for speed, we're going to get a constant increase every single time. For the distance, it's going to be a little bit different because every second we're going faster. And as we go faster, we change our position, not the same. All right, so at the end of 1 second versus 2 seconds versus 3 seconds, think about this. If after 5 seconds I'm going 50 meters per second, and at 1 second I'm only going 10 meters per second. So if I'm going 10 meters per second, then the next second I have only traveled 10 meters. But if I'm going 50 meters per second, then during that next second, I'm traveling 50 meters. So in this case, when we're accelerating, our distance is not changing constantly. Our distance is getting larger and larger and larger every single second. So we can kind of contrast how those things change as the acceleration changes. Give an example of when acceleration could be negative when the velocity was still positive. So if acceleration is positive, that simply means something is, in our normal language, speeding up. If the acceleration is negative, that means that something is slowing down. If velocity is positive, that just talks about the direction in which it's moving. So something may be moving to the right. So if we had an object that was moving to the right, but was slowing down, then we would kind of represent it that its motion was positive because it was moving to the right, but its velocity was negative because it was slowing down. In other words, its speed was getting to be less. Right. We could do the reverse. If something was moving to the left, it would be negative, but if it was speeding up to the left, its velocity would be kind of thought of as positive there. The illustration in this next one is the idea that if something's making a dot at the same space of time, so if each of these dots happens 1 second after the last, the idea is that the distance is increasing. And so if we're increasing distance during the same amount of time, then something's speeding up. Another way to think about this is this would be a falling object. If you took a picture of a falling object, if we turned it around and took a picture of a falling object each second, it would get farther and further apart in each photograph. If you were going down the road and you were speeding up and you were tossing a candy out the window, every second, the next piece of candy would be farther from the last piece of candy. So this is what it would look like if we were speeding up. If the dots were equidistant, they would be constant speed. And if they were kind of reversed, we could get an idea that things would be slowing down if the dots started getting closer together. Vector and scalar are both usually numerical measurements. They usually have numbers to them, but the only difference is that a vector is going to have a direction to it. So vectors are when we talked about displacement. And then when we use displacement over time, that's where we got a velocity. Scalar measurements are just when we added up the distance and we didn't care about which direction things were in. And when we did distance over time, we would get speed, which also doesn't need a direction for that. Next one's another math question. So ball falls for 10 seconds and hits the ground. How high was it? This is going to be a gravity free fall type of question. So let's go through and see all the things that we know. I've got 10 seconds, which is a time. And you just see there's no other numbers given to us in here. If it's falling, we can assume that it started with an initial velocity of 0. We're assuming that it's on Earth, so it would have an acceleration of 9.8 meters per second squared, technically negative. And so the question simply is, how high is it? So we're trying to solve for D. So these are our two that solve for D. This second one is the one we can usually check, particularly with free fall, because I've got an initial velocity, which I have, I need a time, which I have, I need an acceleration, which is there, and then the time shows up again. So for this formula, I've got everything I need. So distance is VIT plus 1/2 AT squared. Because VI is 0, we don't need to include that part of it. So it's really just 1/2 AT squared. A is 9.8, and our time is 10. And we need to square the 10. Be careful in your calculator that you don't multiply everything together and then square it. We're only squaring the 10. So when the 10 gets squared, we've got 100. 1/2 of 9.8 is 4.9. And if we multiply 4.9 times 100, we're going to get 490. And again, we're looking at how high something is. And in this case, we used meters per second squared with our acceleration. So that would be meters. Scrolling down. When we throw a ball up in the air, at the very top of it, it's going to come to a stop. And so that's the speed. So at the top, its speed is going to equal 0. The acceleration of gravity doesn't change at any moment. So regardless of where anything is on Earth, the acceleration is going to be unchanging. Even if you're not moving, like I'm sitting here right now, the acceleration due to gravity is 9.8 meters per second. I'm not moving because the chair is pushing up on me. That's a discussion for a later unit, but gravity is always pushing down with an acceleration, trying to accelerate things at 9.8 meters per second squared. We looked at a video in class with no air present, a feather and brick will fall at the same speeds because gravity, again, is acting equally on them. There's no air to change that up. Gravity will change in different parts of the solar system because different size objects have different amounts of gravity, and different amounts of gravity cause different accelerations. So if we went to the moon, things are going to fall slower on the moon compared to Earth because the moon is smaller. So we're going to get a slower fall, if that's not what I said. So we're going to get a slower fall because the moon tends to be smaller. If you went somewhere larger, the opposite would happen. Higher gravity, greater fall. And then the last one we have here, since acceleration due to gravity is a downward direction, is it technically positive or negative? It's negative because usually when we're doing vectors, down is a negative direction and up is a positive direction. And the number used for acceleration is going to be 9.8 meters per second squared.